Alrighty, so how was it on a scale of 1 to 10? 10 means I got 100. I'm feeling pretty dang confident about myself and my life. That can life. 9, 8, you know how this goes. Okay. So I'm feeling good. Some people got finished in like 30 minutes. Some of you guys need more time. That's not something I would normally do, but this, I'm just ready to be done with Unit 2. I don't know about you, but we've been on this since February the 3rd. I'm ready to start something new. So we had to kind of get this straight, the last thing done, and then we'll review this whenever everybody has taken the test. So, nomenclature, aka chemistry, foreign language. So we're going to learn how to talk that special chemistry language. We got to talk about some of the symbols and ways that you can speak the language. But so you won't, that's what in your note paper that I give you just yet. But I do want to go ahead and talk about the things you already know. I'm going to use some really common examples, some things that you just need to connect the dots with. And then I'm going to teach you how to start naming ionic compounds today. So those of you who won't be here tomorrow, you'll finish up the notes on the video by yourself, sorry, or come after school tomorrow. But then on the homework it says start problem set 9. It doesn't say finish problem set 9 because you won't be able to. But make sure that you do try to start it so that you guys can ask me good questions. So, and then some of you guys, good job. I saw your free responses, 100% done. Some of you guys did not take advantage of that opportunity as much as I thought you would. So we'll see how your multiple choice goes and see if you have any questions you need to ask me then. But pretty much, we need to learn how to talk chemistry and write chemistry. The ways that we write chemistry are with symbols. The symbols you've seen for, I don't know, 10 years of your life probably. Seen the periodic table in random places. But anytime that you see something from the periodic table, then it's just a symbol. And the element name is right underneath it. So if I say W, you say? Tungsten. Good. Some of you guys know that. Okay. W is tungsten. It makes no sense, right? Probably pull out your green periodic table because you've already written down some notes on this. That will be very helpful. So if I say I want an atom of sodium or an atom of chlorine, it's just symbolized by a single symbol. An atom is a symbol. But then if you need to go deeper, you want to give me a whole bunch of symbols together, that will be a formula. So if I say write the formula for something, you don't just write a single element or a single symbol. You write multiple symbols together. So it's just putting a name to something that we've already been doing, for a couple years of our life here. So anybody know the name of this one?
Salt.
Salt is a generic term for anything ionically bound.
Sodium chloride.
Sodium chloride, table salt, thank you. This one? Carbon dioxide. You hear that you just said sodium chloride. No prefixes in there, no like mono, di, tri, tetra, none of that craziness. What did you say on this one? Dioxide, to indicate there are two there. So we're going to be trying to figure out why we use the di and the tri and those prefixes on some things but not other things. So this is definitely a formula. This is sodium chloride formula. This is the formula for carbon dioxide. Carbon monoxide, potassium chloride, calcium chloride, and so forth. So we can keep going on, but we're going to actually learn how to write those now. At the end, though, sometimes you're going to, in our next unit, actually, you're going to have to learn how to put these things together and show how they react, which you do in an equation. So we have sodium, solid, an atom of, actually this is liquid, we have to make it molten because solids don't react very well. We have gaseous chlorine to make sodium chloride salt. That's a very explosive reaction. It releases a lot of energy when that does that. And it makes this lovely lattice, very hard at room temperature, lattice of sodium chloride. You can see that it happens, it compounds upon itself. It's not just one sodium, just one chlorine. Okay, so we've got formulas. The formulas, though, I didn't mention this earlier, come in two varieties. If it's a covalent compound, then we call it a molecule. So that right here, this is a molecule of carbon dioxide. If it's ionically bound, and I'll tell you how to refer to that in a second, if it is ionically bound, we call it a formula unit. We abbreviate that FU. Not being mean, that's just how we abbreviate, okay? So this is a formula unit of sodium chloride. Okay, so we just say different things for different types of compounds. Thumbs up, next page. Okay, I'll give you guys a second. Those are just some vocabulary that you'll be utilizing. So if I say how many formula units do I have, you're like, what the heck is formula unit? It's just something that refers to ionic compounds. Okay, I have this, but I'm going to refer to this after we get through some more here. Okay, this is the longest slide. I've got characteristics of all the characteristics of ionic compounds and covalent compounds. They are almost directly opposite of one another. So I'm going to let you guys at least write down the purple words here, and then I'll explain. At least the purple terms. Obviously, you can write down everything. You take a picture of that. What you gotta do. characteristics of specific categories of compounds. It's not on there yet, 18. Yeah, you just write it on a piece of paper. You're taking a picture. Back here. You guys can't see in the back. Sure. I'm gonna explain all this in just a second. I just have to hush so you guys can focus every now and then. And these notes are already posted online. I always post notes beforehand if you guys want to print them ever. So you got full access. Alright, so I'm going to slowly go through ionic and then we'll do covalent in a second. So ionic compounds, really easy to identify. If you see a metal involved with a nonmetal, it's definitely an ionic compound. No question about it. So the metal, so having a metal plus a nonmetal in a compound formula together will indicate that it's ionic. And if you see that, then you already know it has all of these different chemical characteristics. These are physical characteristics or physical properties and chemical properties in some cases. So called formula units, we already went over that. They have really high melting points. So who's ever put salt, like some sodium chloride, in a pan? Maybe you're seasoning some chicken or something. Maybe we cook. We eat food. Yes. Okay. So if you've ever tried that, you've probably never seen that salt melt. It doesn't just like make a big pile of goo. Okay, it stays as a solid form. Because you would have to get, for example, sodium chloride up to about 2,000 degrees Celsius to melt it from solid to liquid. What's the melting point of water? Melt. Oh, you're not going to say the F word. 0? Don't. That's okay. 0 degrees Celsius is our melting point, boiling point of water. 100, which would burn you, degrees Celsius, right? So 2,000 degrees Celsius is the melting point of these ionic, or in that ballpark of ionic compounds, which is crazy high, right? It's because they have really, really strong attractions for one another. So this gray atom in the middle is kind of hard to point to, so it's in the middle, but it's surrounded by a bunch of other atoms that are all electrostatically attracted to it because they are ions. Positives and negatives totally attract to each other, okay? So they have a really strong attraction, so it takes a lot of energy to pull those things apart and break them apart. So if you do, by chance, break them apart or cause them to go to liquid phase means molten. Think molten lava, okay? We've all played the floor is lava, the ground is lava. Okay, that's, you don't touch the lava. Don't touch the molten liquid. It's very, very, very hot. Or aqueous. Aqueous, does anybody remember what that refers to? Kind of. What's the Spanish word for water? Agua. Agua. Aguas. Yes. Aqueous. Aqueous. I try to make it work, okay? It means just dissolved in water, okay? It just means that the solid you've dissolved in water. So what happens is when these two things, these two state changes occur, the electrons are free. And if electrons are free, what is conducted? I hear you. Specifically, what kind of energy? What does that sound like? Electricity. Thank you. So electricity is conducted if electrons can become free, because electricity is just straight up electrons moving around from place to place. That's all electricity is. So if we can let the electrons go free, they can move, they can conduct electricity. So they're conductive or electrolytic in their molten or aqueous stages. They're definitely solid at room temperature. You don't see like, let me pour some liquid salt onto my french fries. That would be gross. No, so it's definitely solid at room temperature. The crystalline structure just means that it has that really cubic-like structure, like this. And if you look, you can kind of see there's a way I can fracture this. Who has ever put out like a deer salt lick? Do we know what a deer salt lick looks like? Okay, we got some comfort people. Okay, I've seen them. Okay, but they're just like this big, not like this big, and they're huge salt licks, and the deer like it. So you can have salt crystals this big, or a little bitty like you put on like some French fries. Thank you. Okay, so. Anyway, you can fracture them. That's because if I wanted to, I could cut this, like fracture it right there, or fracture it right here, or fracture it here, here. There's all kinds of gaps that I could fracture out, which makes it brittle, meaning that you can throw it on the ground and it'll crack into multiple pieces. Soluble in water, it dissolves. Salt water? Yeah, okay, dissolves. And then how in the heck does all this stuff happen? It's just simply because of that one or more electrons that were donated from a metal to a non-metal. So metals commonly donate the electrons, and non-metals generally do what? Gain them. They take them, okay? Take those electrons. And that's because metals, I'm going to point to this periodic table over here. Metals, lithium, sodium, potassium, rubidium, calcium, strontium, magnesium, beryllium, blah, 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 they're all going to bounce back to noble gases by losing electrons. So are they cations or commonly, or are they anions commonly? Cations, definitely. So generally, you're going to have a metal cation. And then generally, all those nonmetals, where's the laser? I'm hoping I'm not pointing at somebody's face. There it is. Okay, nonmetals all in this kind of upper right corner are going to gain, because they're only like 1, 2, 3 electrons away from noble gas electron configuration, so that's beneficial for them to become like a noble gas, so they gain electrons. So a nonmetal is generally going to gain a negative charge when they do that. And this is all from, that's just from unit 2. But when these two things come together, they make an ionic bond. Okay, so you've heard ionic bonds are caused by donation of electrons. Covalent, so write down the bolded, at least the bolded words here, or more. Tablets, or bring a laptop as long as you're on task. I'm cool with you taking notes, but we have to write a lot of math in chemistry, so it's not like biology where you can just type notes out. So I'm cool with that as long as you're on task. So some of you guys type faster than you write probably. I know I do. Okay, so opposite of ionic is going to be covalent. Covalent, it's really easy to identify as well. It's if you see two nonmetals together. Throw out a nonmetal for me, Lewis. Nonmetal. Hydrogen. Keys, give me another nonmetal. Ooh, those two actually don't work together. Did you say oxygen? Awesome. Okay, thank you. So oxygen there is going to be our nonmetal choice. So we've got two nonmetals, definitely going to be a covalent structure. So anytime you see two nonmetals together, you would say it's covalent. Helium generally doesn't bond with anything because helium's a noble gas. Sorry, my example did not work. Okay, so they don't make ions, they make they make molecules. So you'll call that like a molecule of water. They are opposites, so they have low melting points. For example, water melts at what again? 0 degrees Celsius, good. So it's going to melt or, change from ice to liquid water at 0 degrees Celsius. Volatile. This one's cool. Okay, who put deodorant on this morning? Okay, so deodorant, who put perfume, Axe, some sort of cologne? Okay, why do we do that, miss? Is it for us? To smell good. Now, if I want Logan to smell me, because I have some sparkly perfume. If I want her to smell me, I'm not going to go up and say, hey, Logan, deodorant? No, I'm not going to go do that to her. That would be awkward. So, how do we smell each other's nice perfume scents? Huh? Okay, so sniffing the air. So something's hitting our nose and triggering a response and making us smell something. Our brain just says, oh, she smells like flowers, or he smells like cologne or something like that, okay? The real reason that you can actually smell it, though, is because your body, it's hot. And it's warming up those things you put on your body. And when you walk by somebody, your hot body warms it up, and makes it vaporize. And when it vaporizes, it touches your next person's nose and makes them smell you. So it's just the ability of that perfume or that deodorant to be vaporized makes it smell good. If you put on something that wasn't going to vaporize, you'd be wasting your money because you wouldn't be able to smell anything. So the ability of something to vaporize really, really easily is called volatility, volatile. So if you put on some non-volatile perfume, it would be useless because nobody would smell you because it wouldn't be vaporizing off your body. So if you put on something like something with a lot of covalent compounds in it, you're going to smell nice and pretty. And you don't have to go up to somebody and say, hey, smell my deodorant. Okay, that would be awkward. Okay, non-electrolytic, opposite of ionic, right? So not able to do what? Right, conduct electricity. Because what's not free? Right, no free electrons. Because there's just not, that looks like xenon. No free electrons. because there's nothing available to move. There's no electrons able to move. So covalent bonds occur by sharing. So this right here is water. This bond right here that I'm drawing is a covalent bond, and it's just two electrons that are shared in that location. And that's it. So there's no actual charges here. They just have a shared space where electrons exist. Okay, so we got ionic, we got covalent. We know our properties? Yeah? Okay, let's see if we know our properties. Go here first. Okay, so which ones are electrolytic, ionic or covalent? Ionic. Which ones are volatile? Covalent. Probably soluble? Ionic. So that means in aqueous solution you're soluble. Okay, so these properties go with those types of compounds. What kind of compound is this? How do you know? Because it's a metal. If you see a metal, you automatically say ionic, okay? Ionic, this one? How do you know it's covalent? Right, so this is a metal and a non-metal. This is a non-metal and a non-metal, because these sulfur and chlorine are in the upper right-hand corner. This one? Say again? Ionic. Aluminum is definitely a metal, people, right? Definitely a metal. This one? How do you know it's ionic? Potassium is a metal. It's in group 1A, alkali metals. This one? Right, it's covalent because it's fluorine bonded to fluorine, so two nonmetals, meaning it's nonmetal, nonmetal, covalent. Next one? Covalent, good. So which of these compounds are volatile? Three of them are, right? Volatile goes with the covalent ones, so sulfur tetrachloride, fluorine gas, and oxygen difluoride. Those are all the ones that are covalent. Which ones are ionic? Which ones are soluble? Sorry, which ones are soluble? We got sodium sulfide, aluminum oxide, potassium fluoride. Three of them. So we're going to learn how to name those now. But you got to know the properties so we actually can utilize kind of cumulative everything we need. All right, the next one I skipped, but I'm going to go back to it. I just want to talk through this one. Write down what you want to. But the first thing, like when you look at a chemical formula, you should be able to tell like three main things. First of all, is it ionic or covalent? Loud and proud. Covalent, because you see non-metal, non-metal. You should also be able to tell how many of each of the atom types are present. So how many sulfurs are present? One. How many oxygens are present? Three. So total we have 4 atoms. 4 atoms are utilized to make that molecule. So you're trying to use your vocabulary correctly and stuff. Now I don't have to write a 1 right there because it looks stupid. S1O3 or SO3. Definitely SO3, okay? It just doesn't look right when you put the 1 there, but do know it's not 0. It's definitely 1. So then if you know the compound type, ionic or covalent, then you know all the properties that go with it. So throw me out a property for sulfur trioxide. Properties. Volatile. That actually would be like somewhat poisonous, okay? Because you would smell it and it would actually sit really heavy in your lungs, and you have to do like a handstand to get it out of your lungs because it's heavier than oxygen. Low melting point. Non-electrolytic. Shares electrons to make a bond. Okay, so we can tell a lot about something just by looking at it now, because we're geniuses. We're the smartest people in school, okay? Chemists are the best. I mean, they just know a little bit more. Okay, I'm going to skip the polyatomics for now. I'm going to go back to that, though. Let's do ionic first. Okay, so this is the general procedure on how to write out a ionic formula. Okay, so you might want to write down some of these examples as I go through them. So when you write out an ionic formula, you have to find the stuff involved. So find the symbols on the periodic table. Then you have to know the charges that are associated with those. I mean, whenever this last unit, because we were talking about, oh, like if something wants to be like a noble gas, it's going to gain or lose electrons. So we already know the charges. We just have to kind of trigger our memory here. So I'm going to say the easiest example ever, sodium. Sodium forms a what charge? Positive what? 1, 2, 3, a million what? Positive. See sodium? I'm going to point over here. Sodium is going to bounce backwards and lose 1 electron. Electrons are negatively charged, right? So what's its overall charge now? +1, right? +1, because when you lose an electron, you're deficient of negative charges, meaning you have a positive charge, overall kind of residual charge. So it has a 1+ charge. Okay, next easiest one we're going to do is fluorine. What is its charge? Either I can go backwards 1, 2, 3, 4, 5, 6, 7 and have a 7 plus charge. That's a lot of electrons to lose though, or I can go up 1. Up 1, so what's this charge? Negative 1, thank you. So what happens is, as we look over at the periodic table for me, as we go up, all these are going to have a plus 1 charge, all these are going to have a plus 2 charge, skip. All these have a plus 3 charge. Some of these have plus 4, some of these have minus 4, it just depends. I'll try to help you with that as we go. These all have a what? Minus 3, minus 2, minus 1, 0. Okay, so it peaks at 4 and then goes back down because you're gaining electrons at that point. Okay, so when I put these two together, here's the crisscross rule. This is what you saw in reading guide 9. Crisscross rule says you take the number, the magnitude of the charge, and you crisscross it down to the subscript of those two atoms. So currently these are superscripts. Super means above. I'm crisscrossing them down to be subscripts, which are representing, sub means below. So they're going to be like the little numbers below. So what happens is this one comes down here and this one comes down here. Notice I'm not carrying the sign at all. The sign, once I crisscross them, that means I'm actually eliminating the charge because I'm just now denoting how many of each of these things do I actually need to make the actual molecule. So when I crisscross these together, I get sodium 1, chlorine 1, but doesn't that just look silly? So we write what? NaCl, just straight NaCl because the ones look stupid. Okay, so let's try another one. Calcium. What's calcium's charge? 2 what? 2 plus, because it's losing 2 electrons. You got to think about the electrons being negative, so deficient of electrons means you are positive. Okay, calcium, and then chlorine again. Minus 1, crisscross these charges. So that 1 comes down here, the 2 comes down here. So what's the new compound? CaCl2, thank you, sorry. CaCl2, calcium chloride. Even though they're both ionic, I still say sodium chloride and calcium chloride. They look different because I require a different number of atoms to kind of do the job. Okay, so this makes sense though. If sodium carries a 1 plus charge and chlorine carries a 1 minus charge, what's their overall charge together? 0. They negate each other, right? Okay, if I have 1 calcium, which carries a what charge? 2 plus charge, and I have 2 chlorines, which each carry a negative 1 charge, what's their overall charge together? 0. So notice that these things are neutral together. If I only had calcium and 1 chlorine, the overall charge of this thing would be a plus 1, and that's a flat lie. You cannot have that, okay? So they have to negate each other out, and that's why crisscrossing the charges make these things electrically neutral. That's how we say that, electrically neutral. Just means they cancel each other's charges out. So let's do a harder one. On your sheet, there's a, I don't have my sheet in front of me, and then grab one of these things. There's a polyatomic ion list we're going to start using. We're going to get to the point where we memorize these, okay? It takes a little effort on some people's part. I'm not really good at memorizing. I have to make flashcards and memorize. I also have a link for a Quizlet on our website. I'll show you to help you with that. But if you get these down, nomenclature will be so easy for the next month and a half, okay? Because we're going to be using this new language we're learning a lot. So then you'll be a chemistry master, okay? So look at your polyatomic ion list, put a star on it. That's going to be in the upper right corner of here, okay? So I want you to tell me the formula for sulfate. Let me give myself an example first. Let's go potassium sulfate. So potassium sulfate. What's the charge of K, potassium? Right, so 1 plus because it's in group 1. What is sulfate? Look on your list. So give me the whole shebang. SO4, 2 minus, okay? This example, write down with me because you need to learn how to use your parentheses appropriately. So K plus is potassium. Sulfate is SO4, 2 minus. Put the 2 minus, space it just a little bit away. And then what I always say is polyatomic parentheses. Okay? If I put parentheses, I will never, ever mess up. And I'm just telling you this now because I really need you to use it. If not, you'll kind of start seeing 42s and 35s and all these things that are way too large because if you don't put a parentheses, this number gets mixed up with your new subscript you make. So, parentheses around this sulfate is what I'm saying. Not the charge. The charge is getting ready to be crisscrossed. Don't hold it in. This is the happy family, though. SO4 is a happy family. Do not break them up. Okay, so with potassium sulfate, what I need to do now is take this 1 and crisscross it to the outside of the parentheses. So that's a 1 out there now. And I need to take this 2 and I need to crisscross it to the inside between the K and the sulfate. So that's now a 2. So overall, what's the compound? K2. Say one more time. Parentheses. SO4. Okay, I know in this one it doesn't make a difference because there's actually a 1 out here, but if in the future we'll have some that does make a difference, so if you start practicing now, you'll be good. All right, so that's potassium sulfate. Now, why in the heck is this called a polyatomic ion? Multiple atoms, and it's an ion because it's got a charge, right? There's 5 atoms here and it's got a charge. All right, let's do another hard one like this. Let's do calcium phosphate. Calcium phosphate. Give myself some space here. Okay, calcium phosphate. Calcium, Ca what? 2 plus. Phosphate, PO4. Say again? 3 minus. Okay, so notice that if I'm saying like sulfide, chloride, fluoride, oxide, what's the general ending of all of those? Ide. If I say ide at the end, 99% of the time, I just look on the periodic table. I'm like, oh, oxide? Oh, that's an O. That's an O2 minus. If I say fluoride, fluorine with a what charge? Fluorine gets a what charge? 1 minus. Okay, so the ide just means periodic table. Look for it, get its charge. If I say sulfate, phosphate, chlorate, blah, 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 ate, or ite, those endings sound different. And that's from your memory or from this list. So we're going to really get into the differences here, but I just wanted to point that out early because you'll hear me say like oxalate, hypochlorite, things like ite and ate, they're from this list. Ides are from the periodic table. Okay, so phosphate and carbon, or this thing, calcium. How do they come together to make what formula? You can crisscross in your head. Ca, 3, because this 3 comes down here, okay. Parentheses. 2. Okay, what if I didn't have the parentheses? What would it look like? 42 at the end, and we all know that's a big fat lie. You can't have 42 oxygens. That would be insane. Okay, so this is a little bit more tricky because you have to kind of think about this and that at the same time, but I think you guys are smart enough. You guys are like my smartest class ever. Smart cookies. Okay, let's do, oh, look at this. This is just, make sure we all know how to get valence electrons, how to get charges. We know how to get this. We've just been doing this for like the last 5 minutes. You want to get an electron configuration of 8 valence electrons, you gain or lose to get that. We need to do transition metals though. Actually, we'll do transition metals next time. Let's do these. Okay, I want you to tell me the formula of these. So this is on your sheet, okay? And I'll skip around. We'll do like 5 examples maybe. How much time? We got 7 minutes. Okay. Let's do 5 examples. And then we'll go back and do transition metals tomorrow. All right, so calcium, charge 2 plus, oxalate. You hear 8, where are you looking? Okay, on the polyatomic ion list, go for it. All right, C2O4, 2 minus. Oxalate sounds like I made it up. I didn't. This is oxalate. Okay, oxalic acid is a very hazardous acid. Okay, so here's our calcium and oxalate. How do they come together? 2 comes down here, 2 comes down here. What do you get? Parentheses 2. Okay, so you see that. Do you notice that we have a 2 here and a 2 here? So that's saying for every 2 calciums, I need 2 oxalates. What does that reduce to? 1 to 1, right? It's a ratio. 2 calciums to 2 oxalates. Well, that's the same thing as saying 1 calcium to 1 oxalate. So anytime you have an ionic compound and you can reduce these subscripts, you have to. It's called the empirical formula. It's the simplest ratio in which they can exist. So we have to reduce this to Ca1, parentheses, C2O4, 1. But this is the more appropriate formula. That would be considered somewhat wrong. It's just a kind of simplicity part of it. All right, aluminum permanganate, my favorite. Aluminum, go for it. Al what? 3 plus because it's in the 3rd group. We bounce back 3. Permanganate. It's a pretty purple color. Mn
Oh,
4.
4.
1 minus? Yeah. Okay, so where are we finding these guys? Polyatomic ion list, right? Permanganate, you will never find permanganate up there. You'll find manganese and you'll find oxygen, but you won't find the combination. So that's why you have to have both lists, or periodic table and that in front of you. Permanganate's a really pretty purple color. It's actually used as an antiseptic if you're out in the wilderness and you have nothing else to drink. Put a little drop of permanganate in your swamp water that you found to hydrate yourself with, and it'll kill the bugs. So, but don't recommend drinking large amounts of it. Somebody drank some in my class one time. That was fun. Okay, aluminum, put it together now. What's next?
1.
Okay, 1, I'm not going to write that. Parentheses. And 3. Okay, so if you went backwards, who does this 3 truly belong to? Aluminum, right? And that imaginary 1 truly belongs to permanganate, right? Okay, so let's go. I'm going to go down to, these are all polyatomics. Polyatomic, poly. Oh, no, lied. Let's do number 6. All right, lithium. Li, charge. 1 plus, because it's on your first row of the periodic table, or first group, so you bounce back 1. Carbide. What does that kind of sound like? Carbon. Okay, so it's carbon. Carbon, since it's in the back here, what's the charge? Is it +4 or -4? -4, because ionic compounds come with two different charges, right? So if lithium takes the cation, the carbon has to take the anion. So when you crisscross them, what do you get? Li4, C1, good. That one looks awkward, but that's lithium carbide. And notice that we looked in the periodic table for that. We did not look in our polyatomic ion list for that. All right, let's do another one from the periodic table. Let's do number 8, aluminum fluoride. Aluminum, I know you know the charge now. Al3 plus, fluoride. That's just fluorine, right? Fluorine with a what charge? 1 minus, crisscross, what do you get? AlF3, right. This 3 goes to the outside of the fluorine. All right, take 2 minutes and go through some more of these. I will say do not do the ones with these Roman numerals in it because you don't know how to do this yet, okay? We'll do those tomorrow together. Don't do the ones with Roman numerals. So don't do the ones with Roman numerals. Try a couple of these so you have some confidence here. I'll come around with questions if you need it.